thread of today's talk, which is this wonderful mineral zircon, which is, of course, the gold standard for geochronology in very old rocks, but also has many other geochemical characteristics that we can use to try and do our geological sleuthing. I like that term. And then the third thread is technological. In order to study zircons, which are very, very small, we've developed new procedures using a new type of an ion microprobe that I'll describe about a little bit later in the talk. So as you might expect, there are a lot of people who have been involved in this work. All of these people either are presently or were at the University of Wisconsin when they did that research, with the exception of Simon Wild, who's at Curtin University in Western Australia, and John Craven, who's at the University of Edinburgh. So mostly these are Wisconsin people. So this is the view of the Hadean Earth, as it's very commonly portrayed both in the popular press and in quite a few textbooks. This is a painting from about 1952, but it shows the moon much closer to the Earth. There aren't Mare basalt lavas yet, so the craters are bright. The Earth itself is covered in magma oceans, and the first bits of crust are possibly floating rockbergs in this magmatic ocean. There's a very intense meteorite bombardment, and the water that exists on the Earth is in the form of steam rather than in liquid water. So this is truly a Hadean condition, and the question is, how long did that last? And so many people have thought that it might have lasted to 4.3, or I've seen estimates as late as 3.5. There isn't very much to support that, and that's really what we want to be discussing today. So here's a linear timeline, and the period of Earth that we're discussing starts at about, or finishes at about 3.8 billion years ago and goes back to the age of the solar nebula. And this is a period that's sometimes referred to as the geological dark ages because there are no rocks older than 4 billion years. So our ability to know about this period from analyzing samples is very limited. The amount of time here, a little bit over 500 million years, is symmetrically satisfying because it's also it's about the same length as the entire hard shell fossil record that we have on Earth. So this is a very significant portion of Earth's history, and one which we know comparatively very little about. But there are a lot of interesting things that have happened in this earliest part of the Earth's history. The core segregated. We believe, most people think that the moon formed by a giant impact at about the same time. The first rocks are dated to here. The first chemical sediments, which indicate presence of liquid water on the surface of the Earth, are at about 3.8 billion years in Western Australia. And then the first putative fossils of microbial life are at 3.5 billion years. And with a few exceptions, most people accept the evidence at 3.5 as indicative of life. So there are a lot of things we'd like to understand about this time in Earth history. So here's the duality. Was it a Hadean early Earth during that first 500 million years, or was most of that time relatively cool with tectonic processes that we might recognize today and with liquid water on the surface of the Earth? And some of the reasons we might like to know about this is that it relates to questions about when did the first differentiated igneous rocks, first granitic rocks form, when did the first continents start to form, and ultimately, when was the stage set for the emergence of life? So the areas where one finds the samples of this very early processes are scattered, but the first fossil evidence, the oldest fossil evidence, is here in northern part of Western Australia in the Pilbara Craton, where these are about 10 micron in scale. These microfossils have been identified and worked on for many years by Bill Schopp and other people. That's at 3.5 billion years. The first chemical sediments are from Greenland, a place called Issawa, where there are sediments called banded iron formations right here, right up against the inland ice, that date to about 3.8 billion years. The first rocks are from Acasta in northwestern Canada. And then the oldest materials we have from the Earth are from this place, the Jack Hills, that by coincidence is not that far from the Pilbara, but is in a separate geologic block called the Yilgarn Craton. And it's the Jack Hill samples that I want to talk about today, because those are the only samples we have that are older than 4 billion years from the Earth. So to get to the Jack Hills, one typically flies to Perth and drives about 500 kilometers up the Great Northern Highway, which is paved, and then you go 200 kilometers down this road, which at the time I went in was not paved. It has now, I think, been made to macadam. And so the Jack Hills are here in the northern part of the Yilgarn Craton in a subunit called the Narrier Gneiss Belt, which has experienced slightly higher grades of metamorphism. And old zircons have been found at the Jack Hills, at Mount Narrier, and then a number of other areas, including the Maynard Hills, within a radius of about 300 kilometers. Zircons older than 4 billion years. So this is false color satellite view showing the Jack Hills. That's about 80 kilometers. Here in the same scale is a simplified geologic map showing in red areas where we've collected rocks to get these zircons. The zircons occur as detrital grains within clastic sedimentary rocks. So the rocks that contain the zircons are themselves much younger, and it's because we can date the zircons that we know that they are older. So they are merely simply grains of sand within this older rock. And there's a little bit of relief here because it's a major siliciclastic unit. They're coarse conglomerates and sandstones that are erosionally resistant in an otherwise very flat area. The closest building is this barn at Mylura Station that's some 50 kilometers away from the locations that we'll be discussing. And in particular, I'll be talking about samples from an Arredondo Hill right here, which is where many people have gone to get old zircons. But we have found old zircons in many of these rocks up and down the range. So I used the word range rather advisedly. This is what the Jack Hills look like. When you get to the end of that road, the road peters out to a track. And even in Wisconsin, we'd barely use the word hills to describe these things. It's very flat Precambrian terrain. So this is looking north towards Mount Hale, and this is Arredondo Hill taken from the air. And so this is what these clastic rocks look like. The history of the rocks themselves is that they were metamorphosed at about 2.6 billion years. We believe that the deposition age was about 3 billion years. And then the detrital zircons that are found within the rocks range from 3 billion all the way back to 4.4 billion years by uranium-lead age. You can see that these are, in some cases, quite coarse conglomerates. Other times, they're cross-bedded sandstones. They're chemically very mature. So SiO2 would be greater than 95%, sometimes 98%. Small amounts of potassium and aluminum, which is now in the mineral muscovite, which is often green because it picks up a little bit of chromium. Up to 5,000 parts per million chromium is dominantly in detrital chromites, and then the zirconium of this rock is in the detrital zircons. And so that's the element that tells you how much zircon are in these rocks. If you crush a kilogram, you'll get between 1,000 and 10,000 detrital zircons if you separate them. So zircons, of course, can be very large. This is zirconium silicate. They can be very pretty. But the zircons that we study are neither of those properties. They're these very small, malformed zircons that one gets out of detrital sediment. So this is a pile of approximately 1 million zircons, not from the Jack Hills. And this is what one of those zircons looks like on Lincoln's nose with a human hair for scale. So these things typically measure about 100 by 200 micrometers and have been variably rounded by the sedimentary transport. One of the reasons that we like zircon, of course, relates to the fact that zirconium and lead are similar in ionic radii, whereas lead in the +2 state is much larger. So when this mineral forms, it tends to scavenge uranium but exclude lead, which resets the isotope clock very nicely. So this is the area, this is the place on Arredondo Hill where most people have been getting their zircons. And that outcrop is now about as high as the Hammerhead. It's been ravaged by collectors, and it's fortunately now protected. But that's a coarse conglomerate, and you separate these zircons, and you can date them in situ by ion probe or by other methods. And this is a false color CL image of the zircon that has yielded the oldest concordant ages, and it's a little bit clipped, but that's 4.4 billion years from this spot. These are ion microprobe spots. and 3 other isotopically concordant spots are within about 50 million years of that age. This is what the data look like on a typical Concordia diagram, and those are the concordant or 99% concordant ages. If we were in a strictly uranium-lead geochronology thing, and I'll probably hear about this from Paul and Warren later, we could spend a lot of time talking about the meaning of those 2 ages. And are they, in fact, 2 different ages, or should we just say these are 4.38 plus or minus 20 million years? So do we believe that these are actually real and discrete ages? I'll show you in a minute that there's reasons to question that. But nevertheless, that is the oldest age, and whether we want to call this 4.38 or 4.40 is not something I'm going to worry about too much. 20 million years, 4.4 billion years ago is a small percentage. There are now about 12 zircons that have been dated by 4 different labs that are, if you round them off, are 4.4 billion years, within 25 million years of 4.4. So the antiquity of these zircons is not in question, although we can discuss the fine points of the geochronology. You notice also that there's a lot of recent lead loss. Most of the spots that you date, this one crystal has been dated 14 times. Most of the spots have experienced recent lead loss, which we believe is the modern lateritic weathering that these rocks have experienced. So one of the first things that we did in the Jack Hills was to measure the section and then to collect samples in the context of section. This is Aaron Cavosi, whose PhD was on this topic. And this is the section at Arredondo Hill showing the sandstones and conglomerates and cherts, and at the very top, a banded iron formation. And so from 5 different layers within this rock, we've extracted zircons and dated them. And this is the histogram of age for each of those samples. These numbers down here correlate to actual igneous rocks that surround the Jack Hills, where you can get a full sample of a granitic rock and extract the zircons. So these are known magmatic ages. And you can see that about 90% of the zircons out of this younger clastic rock could be explained as just eroding granites that are nearby. That doesn't prove that that's how it happened, but it could be. But what's of interest to us is this small peak on the histogram over here. Between 5 and about 15% of the zircons that you date have these ages that are older than 4 billion years. And there are no known rocks that have that age. They've apparently all been destroyed or have not yet been identified. And that's what we're really most interested in. This sample is different, however. It contains these younger samples, zircons that are younger than what was believed in 2001 to be the depositional age of the rock. It's now recognized that there's major fault in here in the sequence, and that this is actually a different siliciclastic unit, a much younger rock. And you notice that the old zircons are absent in that rock, just a small number of meters away on Arredondo Hill. It's much more complicated than we originally thought. So this is what the zircons look like. Each of these is one of those 100 by 200 or 300 micron units. This is laid out on double sticky tape preparatory to casting like this. This is a 1-inch round epoxy mount with 1,500 zircons in it. I can't do this, but Aaron Cavosi would stop drinking coffee on Tuesday, and by Thursday he'd be able to place them down in a nice row like that. This is very nicely done for analysis. But you notice before they're cast, you notice that while some of them still have crystal faces, they're all rounded because these are detrital, and some of them are almost spherical. They've been abraded so much. And my sedimentology friends tell me that you can't do this with water transport. They're too cushioned, and this requires aeolian transport. They must be wind blown in order to be rounded that much. So after they're cast, you can image them by cathodoluminescence on an SEM, and you see this wonderful internal texture that those of you who work on zircons are very familiar with. There's a lot of variability here, from sector zoning to pretty nice, consistent, concentric magmatic zoning. Some of these zircons, when you look at them this way, have had a tortured life, and we do see evidence of radiation damage in quite a few of these zircons. And this is a list of the different sorts of analyses you can do on zircons once you've mounted them like that. There actually are some other things that I'm not going to talk about today because we don't have enough time, but I'm happy to answer questions. But we'll talk about the imaging and the geochronology, and then oxygen isotope measurements, and then trace elements, including lithium and titanium, and lithium isotope ratios, and then a little bit about some of the minerals that are actually included within these zircons. There's really a lot you can do with a grain of sand. So here are two very contrasting zircons, one that has good igneous-looking texture, fairly simple to interpret, an older core and a younger overgrowth. The ages are all the same. In the core, the overgrowth is about 3.7 plus or minus something, which is the oldest rock in this part of Australia. And then these are oxygen isotope ratios correlated as closely as we can aim the ion probe, correlated with the geochronology spots. And so we see it's homogeneous in oxygen isotopes also. Here's a very different zircon. It's a bigger zircon. We analyzed it to death because it yielded this very early age, older than 4.3 billion years. It has a 3.7 billion year overgrowth also, but in the core we see that the concentric zoning tells us that this is the oldest part of the zircon here. It was very much broken off and abraded before that overgrowth grew, and that the stratigraphy of the zoning tells us that it gets younger going here. And yet here is the oldest age we've measured. It's basically concordant, 1% above Concordia. And we see other ages, including one here at 4.15, that are closer to the center of the zircon and younger. That's not supposed to happen. So there's some sort of a complex discordance and resetting that's happened in this zircon that's not well understood. And we've seen a number of zircons that do this, but they don't all do this. And the take-home message is that you must do the geochronology correlated with the CL and with other types of analysis in order to sort out which of these zircons are better preserved and which ones are questionable. So there is some complication, and then here's resorption you can see, and probably radiation damage. It's a complicated thing. So the work that we're doing in Madison is on this instrument. This was the first of the Kamika 1280 series. It's a large radius ion microprobe. The reason we use this is that it allows us to make these very, very small spots into the surface of a polished mineral grain so that we can observe textures and then we can correlate our geochemistry one to another. And when we do this for oxygen isotope ratio, we typically are measuring a 10 micron spot, although we can do it as small as a micrometer. And we're analyzing in the range of a nanogram to a picogram of zirconium silicate. And on a weight basis, that's between 1 million and 1 billion times smaller than what we've been doing for 30 years in what I call my conventional lab at the University of Wisconsin. So the ability to analyze these very, very small samples has really been quite important for us. So in its simplest form, this is what an ion probe does. You have a sample, and you bombard it with a highly focused plasma. For oxygen isotopes, we use cesium ions, and then material is sputtered off, and some of the material that is sputtered is accelerated as the secondary ion beam. And so that is the SIMS. It's a secondary ion mass spectrometer. And here's the instrument itself. There's the sample. This is the primary beam. The secondary ions are then focused twice, first by an electrostatic analyzer, which sorts for kinetic energy, and then by a 3-ton magnet for mass over charge. And we have a series of 11 detectors on movable trolleys, and we can then simultaneously analyze oxygen 18, 17, and 16, although most terrestrial samples we don't bother with 17. Sorry? We can do lead. The mass dispersion here is about 17%, so that if we're doing oxygen isotopes, we can't be doing lead unless we change the magnet field. For the highest precision, we always choose one system. So when we're doing oxygen isotopes, we set up for oxygen isotopes. It takes about a day to stabilize the instrument, and then we don't do anything else until we're done. We could do lead with this instrument. When the detectors are closest together, we can analyze adjacent lead isotopes. So this instrument is fully capable of doing that. But in fact, we choose to go somewhere else where there's a lab that 24/7 only does lead isotopes, rather than to do this in our spare time. Yeah. But this is the sort of instrument you would use for in situ geochronology. Yeah. So the ion probe is a very versatile instrument. One can analyze all of these elements. The primary difference being what the primary beam is, whether you're using a cation or an anion to optimize your your ionization. We don't try to analyze all of those things at Wisconsin, but we concentrate on isotope ratios of this suite of elements, the light stable isotopes, and we do a little bit of trace element work. And so mostly I'll be showing you oxygen isotopes today, which are, of course, reported in this normalized delta notation, which is the 18-16 ratio in your sample normalized to a standard, which is ocean water. So we also do all these other things. I'm not going to talk about any of this. Some of you might prefer I would talk about some of these other topics, but I'll be talking just about zircons. But we work on a lot of things that you would expect a petrologist, an igneous, a metamorphic, or a sedimentary petrologist to work on that are perhaps conventional applications. But we're increasingly getting drawn into various records of paleoclimate, forams, fish ear stones, stalactites and stalagmites, speleothems, and we're starting to get into analysis of things like single bacteria, in this case a symbiont on a larger animal, and even analysis of brain cells. There are a lot of things you can do with an ion microprobe besides zircons. So the ion probe has a reputation as being a finicky, difficult, hard to use, some people would say unreliable instrument. And that's not altogether unjustified. This is a technique that has evolved and improved very significantly over the last 30 years. And so just to show you what has been the state of the art for oxygen isotopes, this is the spot-to-spot reproducibility, or the precision, if you will, for oxygen isotopes. And 30 years ago, it was plus or minus 10 per mil. 1% was the best you could do at one standard deviation. And that was using an instrument called the IMS-3F. And as new instruments became available, the precision dropped from plus or minus 10 per mil to plus or minus 1 per mil to 0.3 per mil to now we can make these measurements at 1 sigma at plus or minus a tenth of a per mil reproducibility. At the same time, the spot sizes have gotten smaller from about 30 microns to 10 microns for that sort of data. And it's become much faster to where we can make these analyses in about 3 minutes now. So it's been a very important sequence of developments. This is what a day, or actually 2 days, of oxygen isotopes look like if you run 24 hours around the clock. So this was a postdoc from the USGS, Brian Rusk, who came to our lab with no previous ion probe experience. And in 48 hours, 2 people running back-to-back made a total of over 650 analyses. The way we do that, and this was all on quartz, the way we do that is to run a lot of standards. And the standard data, this is the Delta 018. The standard data are shown in blue. That's actually 4 analyses as a cluster. And then, so we do standards, and then we do some samples, and then standard sample. And you can see that while the samples are varying by some 40 per mil, these are hydrothermal vein deposits, the standards are rock solid for all 48 hours. So I'm not just showing you our best 10 analyses cherry-picked out of a lot of analysis. This really is something that can be done routinely now, hour after hour. And when you do this, you get this precision at 2 sigma that's better than 0.3, which is 0.15 or 0.1 at 1 sigma. And you can drive the standard error down to almost anything you want, depending how many analyses you do. So here are the oxygen data for these Jack Hill zircons. These first data that we measured were on a 4S instrument that was not quite as precise. And so this is Delta 18. These dashed lines show you that, in fact, with the exception of these aberrant spots that I've X'd out, the data all fall within a very consistent field of about 5 or 4.5 to 7.5 per mil. And even the authors of this paper, who were the authors of this paper, no longer interpret these high Delta 18 values as being igneous and magmatic. So there's really now a uniformity of all of the people who work on the Jack Hill zircons that this is the range in values. What we reported 10 years ago is, in fact, the range, although the histogram is much larger now. There's a lot of new data. And it happens to be that that's the same range in oxygen isotope ratio that we see of zircons throughout the Archean. This is not a surprising range compared to younger rocks. Now, if we compare the range of oxygen isotopes, this is now expanding the scale, in the Jack Hills, which is this field, to what we know about the oxygen from primitive components on the Earth, we see that it's really quite different. So olivine out of mantle xenoliths, olivine from ocean island basalts. This yellow band is the same on every one of these fields. This is what we now call the mantle oxygen field. Zircons that are megacrysts out of diamond pipes that have been brought up from the mantle fall within this field. Zircons that are actually more common than most people think in young modern ocean crust fall within this field. And in fact, the moon also falls within this field because the moon and the Earth are isotopically homogenized. And the Jack Hill zircons are really quite dramatically different. They have this, what I would call a mildly enriched oxygen isotope signature. And if we found this signature in younger rocks on Earth, there would be nothing surprising about it. We see high delta O18 igneous rocks very commonly. And we would interpret that as interaction on the surface of the Earth where fractionations are large. The only thing that's surprising about these zircons is the antiquity, the age at which we find these high delta O18s. So here is now scanning out, here is oxygen isotopes from a lot of surface and some igneous sources. These are zircons, but these are sediments. And this red band now, which is very narrow, is that wide band that was the mantle range in the previous slide. And so there's the mantle, that little green thing that you can't see. And we see these very high delta O18s very commonly on the surface of the Earth because at low temperatures, the fractionations become quite large for oxygen isotopes. Whereas at mantle temperatures, at high temperatures, the fractionations are small, and you can't create that mildly enriched signature that we see in the Jack Hills unless you're on the surface of the Earth. And the processes that cause these high delta O18 values are things like weathering and very low temperature diagenesis. They are all mediated by water. So this is the basis of the cool early Earth interpretation, is that we are seeing oxygen that was fractionated on the surface of the Earth that was then buried with material which melted to form, I'll show you in a minute the evidence, granitic magmas, which then crystallized these zircons. So it's a fairly complicated scenario, all of which was going on the earliest Earth, just as it's going on in the modern Earth. And just to drive home that point, that these are the Jack Hills data, there's really nothing unusual about these compositions except their age. This is uranium-lead age for zircons from about 1,200 different rocks from modern all the way back to 4.4 billion years. And this is the delta O18, the oxygen isotope ratio. And throughout the Archean, the whole first period of Earth history, we see zircons that have either the mantle range, which is these two lines, or mildly enriched. And we see that throughout the Archean. And so the processes that were going on when the parent magmas of the Jack Hill zircons form are the same as the processes that were going on throughout the Archean. And in fact, something very different started to happen in the Proterozoic at around 2.5 billion years, which probably relates to weathering and may in fact relate to the rise of oxygen in the atmosphere and the blossoming of photosynthesis and biological activity. But throughout the Archean, the oxygen, as it recycles into magmas, is very, very constant. Now, what I've just told you assumes that when we measure the oxygen isotope ratio in a zircon, the values we measure today are the same as the values when they were in the magma, that the compositions have been preserved and that they haven't been changed by some process. And one could challenge that based on diffusion experiments. These are the Watson and Cherniak experiments on oxygen diffusion rates in zircon. And as you'd expect, under hydrous conditions, the diffusion is faster than under dry conditions. That's the log of D there. And if you take these hydrous diffusion coefficients and you calculate the closure temperature for something so very, very small, you get for slow cooling rates closure temperatures of 500 or 600 degrees, which would make you worry that maybe the oxygen isotope ratios we're seeing in these early zircons have been acquired later by diffusion. But one thing that makes us think that might not be the case is the uniformity of these early zircons. If these zircons were being affected by diffusion, and this is really the range of values that you expect, it doesn't make sense because you don't put the toothpaste back in the tube. When you see secular trends like this, if it's the older rocks have been more altered, what you normally see is that younger samples are tight And as you go further back in time, the range in values becomes more extreme. So we see a consistency here that made us very early on suspect that these zircons were preserving their oxygen. But we've nevertheless done a lot of tests to try and evaluate whether these wet diffusion data are in fact controlling the preservation in our samples, or whether in fact this is really the diffusion law that applies. And so one of the things we did was to look at this zone zircon, and we've looked actually at quite a number of zircons like this. This is small like all the others, and it's got this igneous core, and this black overgrowth is also zircon, but of a metamorphic origin. And we've dated it. This is 1.3 billion, and this is 300 million years younger, forming during Anatexis. This is from a granulite facies migmatite, a rock that partially melted, and then the metamorphic zircon grew from that melt. And so that's the size of a shrimp spot. This is the size of a 10-micron oxygen isotope spot, and we very early on found that the delta 18 here is 6, and here it's 12 per mil. So there's a big difference, which makes perfect sense because of the sedimentary protolith of the migmatite. And we wanted to know how sharp that step was so that we could model the diffusion that would have occurred after the overgrowth formed. And with the 10-micron spot, it was too sharp. We tried a 7-micron spot, and it was too sharp. And so what you see here is an array of 35 spots, each of which is smaller than 1 micron in diameter, so that we could see what that profile looked like across this gradient. And here is that array of 35 spots. Here's an enlargement of 2 of the spots. They measure half of a micron by a micron. We didn't know how deep they were because it's only the wavelength of light across, so we cut this one in half with a fib, and it's about a micron deep. So each of those analyses is a half of a cubic micrometer of zircon, a couple of picograms. And this is what the data look like. So there's the high delta 18 overgrowth. There's the low delta 18 core. If you assume that this was a perfect sharp step to begin with, then the error function there is the diffusional relaxation over the history of the zircon. And from this, you calculate a diffusion coefficient that exactly agrees with the dry diffusion. It doesn't agree with the wet diffusion rates. And it suggests that the closure temperature is above 800 degrees. We've done similar profiles in upper amphibolite facies zircons, granulite facies zircons, and high-temperature eclogite facies zircons. And it appears to be the rule that you see these steep gradients, and that the diffusion genuinely is very slow, and that therefore over the age of the Earth, the oxygen isotopes in these zircons are basically forever. Now, if you have a radiation-damaged zircon, or if you had a zircon that had gone to sapphirine facies, 1,000-degree metamorphism, which is a fairly rare thing, then this might be violated. But if it's only been to partial melting, the zircon will preserve its oxygen isotope ratio, according to all of the results that we have. So now I want to show you something else. We've done a fair amount of lithium analysis now in zircons. We weren't sure we would find lithium initially. It turns out to be quite common in some zircons, but not all. If you take zircons from the mantle or from ocean crust, or these kimberlite zircons, they have typically a couple parts per billion, with a B, billion lithium. Here it is in parts per million. But when we measured the Jack Hill zircons, we found that they were very much enriched in lithium, between 10 and 70 parts per million. This was a little bit of a surprise, but lithium is incompatible and concentrates in granitic and pegmatitic magmas. These are some early data for other examples of continental crust, and we've now shown that zircons from continental crust are very much enriched in lithium on a parts per million basis, 3 to 5 orders of magnitude. We've also been able to measure the lithium isotope ratio. This is work done by Taka Ushikubo and others in my group. The Jack Hill's data are here, measured by ion microprobe. And then all the rest of these lithium isotope data are, in fact, published data from rocks from other labs, principally University of Maryland. And what we see is that the lithium isotope ratio in primitive rocks is very tight, clustering right around about +3. In altered ocean crust, it's a little bit more variable. In continental crust from igneous rocks, it's a little bit more variable still. But if we look at weathering products in continental crusts, we see that it's quite variable, from about +15 to -20, and that this range in values happens to overlap very nicely with the range that we see in the Jack Hills. lithium isotope studies are fairly new, and this is a very small data set. But if we believe that these are laterites and saprolites, if we believe that that's representative, then the suggestion is that the protoliths that these zircons came from in the earliest Earth were a heavily weathered environment. The cause of this fractionation is thought to be lithium isotope chem-absorption on the aluminum oxides in the weathered material. And so the suggestion is that in the earliest Earth, that igneous rocks were deeply weathered, and that was the high delta O18 material that was buried and remelted. We're working on quite a few things to try and test that further. If that's correct, though, it makes a lot of sense, because the earliest atmosphere may have been as much as 3 bars of CO2. And while I call it cool, it may in fact have been 50 or 70 degrees. It may have been a very acid sauna, a very aggressive weathering environment at 4 to 4.4 billion years ago, in which case this sort of weathering would be what you might expect. Now, as for oxygen, we've worried a lot about whether the lithium is preserved in the zircon from the time of formation or whether it's been acquired later. What this shows you is that neither the age or the delta 7 or the concentration in parts per million is affected by whether the zircon is 100% isotopically concordant or whether the uranium-lead ages are slightly reset. So less than 98 means 85 to 98% concordant. This is the agreement of the uranium-lead ages, which is a measure of that lead loss that we saw earlier. So the concordance does not correlate with these results, which is encouraging. But what's more encouraging is that the lithium concentration correlates with the zoning, with the CL zoning. And so this is subtle to see, but here's a small area in the zircon, getting back to this point that you need to correlate what you do. Here's the CL banding is vertical in this zircon, and here's lithium mapped with a scanning ion image on the ion microprobe. And we see that the lithium-rich band here correlates with the banding. Here the banding is horizontal, and here is horizontal band. There's a feature here which is a little bit more lithium-rich. The lithium-rich domains correlate with the dark CL, which is also more enriched in the rare earths, uranium and thorium in zircons. And so when you see dark and light, there's a feature that comes down here, which if you look closely, you can see there's a feature here, which is this. When you look closely, you can see these features. Now, one thing that throws people off with these images are these cross-cutting lines, which are the cracks. And the cracks look like they've been leached of their lithium, but that's in fact not what we're seeing. What we're seeing is the different depth of field of the two techniques. So if you think of each of these cracks as being V-shaped, like the Grand Canyon, the SEM sees right to the bottom because it has high depth of field, and you're looking at the Colorado River. The ion probe has very low depth of field and is imaged on the plateau. And so what we're seeing here are the north and south rim. And so the ion probe makes this crack look wider, but it's only because of the relief effect here. And so the main feature here is that this is lithium rich and this is lithium poor, and that correlates with the CL zoning that we see by other means. So the lithium has been preserved and correlates in this way. Now, we worried a lot about where the lithium actually was, because you don't normally think of lithium in this mineral. This is the ionic radius, Shannon and Pruitt radius of lithium. It's very similar to zirconium, which makes one think that it might substitute for zirconium. It's very similar to the rare earths. It's been known for a long time, though, that there's a charge balance problem with putting non+4 cations into zircon. And that's seen here as a plot of the +3 cations versus phosphorus. And so the xenotime substitution, which would be one phosphorus coupled with a +3 cation, would suggest that you have a 1-to-1 relation when you make this sort of a plot. And it's been seen by many people that there's not enough phosphorus to charge balance all of the rare earths that we find in zircons. And so this is telling us that there's something going on. And if we were to stick lithium into the zirconium site, that way exacerbates the charge balance problem. So what we suspect instead is that, in fact, the lithium is going into an interstitial site, as proposed by Fitch and Hanchar about 10 years ago now. And in that sort of a situation, the +1 lithium charge balances the rare earths rather than enhancing the problem. And in fact, a small amount of lithium does a lot of charge balancing because of the differences in atomic weight. 10 parts per million of lithium would be equivalent in charge to 200 ppm of the rare earths. What we believe is that, in fact, these coupled substitutions are active, and that the lithium is going into an interstitial site. But it's quite likely that the lithium is, in fact, going into more than one site, and it may also be substituting in the zirconium site. There's a lot of concern about lithium diffusion rates, because there's been much published that shows that lithium diffuses very quickly in a lot of geological materials. In silicate melts, lithium, in fact, moves faster than helium, according to Richter's work. And even in clinopyroxenes, there are zoning profiles that have been measured in situ that suggest that lithium moves quite quickly. But if we believe, or if we're correct, that lithium is being charge balanced by the rare earths, then the concentration of lithium in zircons will be partially locked in by the very slow diffusion rate of the rare earths. And so here now is the diffusion coefficient of rare earths, and they are very, very slow. So it's possible that the lithium is locked in as an element by this coupled charge balance substitution. So if we use new diffusion data that were published about 2 months ago by again, Bruce Watson's group, we see that, in fact, lithium in zircon diffuses very much more slowly than helium. It's 8 orders of magnitude different than the relationship we just saw for silicate melts. It's almost as slow as oxygen, but still these data suggest that the closure temperature would be around 400 to 500 degrees. And so the diffusion experiments are now consistent with the possibility of preserving lithium over geologic time, but it's not very compelling. And I still think that the most compelling thing are that we see these lamellae preserved. And if you use these experimental data to calculate preservation criteria for lamellae, a 10-micron lamellae in a rock that was at 450 degrees would be preserved for about 10 million years. And what the diffusion data are suggesting is that these rocks were never metamorphosed to a higher, the zircons rather, were never metamorphosed to temperatures higher than that. So I've got to go fast now, and I want to just sort of summarize some questions we could ask using these sort of data, starting with things that we probably all agree on and moving towards more and more contentious questions. And there are a lot of contentious questions about these Jack Hill zircons. People used to ask me how we knew that they didn't come out of meteorites when we only had a couple of these zircons. We have so many of them now, and the ages are so different that that's not really a question. But because of this, I measured the oxygen-17 ratio. And everything on the Earth falls on this line, the terrestrial fractionation line of 17-16 ratio versus 18-16 ratio, because they're mass-dependent fractionations. It's only in meteorites and other objects in the solar system that we see things that plot off of this line. So, for instance, carbonates in the Allen Hills Mars meteorite are significantly different, even by ion microprobe. To my knowledge, this is the first time that it's been possible to distinguish Mars from the Earth by ion probe. It's previously been done with conventional large sample analyses. But we see that other bodies in the solar system are dramatically different, but that the Jack Hill zircons fall right on the line that we predict for the Earth-Moon system. Are these zircons from the Moon? It's been said by a number of people, well, zircons form on the Moon, and that doesn't require, there weren't ever any liquid water oceans on the Moon, so why do zircons on the Hadean Earth suggest something different? And the point is here that the zircons that we find in the Hadean are really quite different geochemically from the zircons on the Moon. And so I've already showed you the oxygen isotope data. The Jack Hills have this mildly enriched oxygen isotope ratio, which we don't see on the Moon. But we also see differences in trace elements, for instance, titanium. And so the titanium concentrations in the Jack Hills zircons are in the range 5 or 10 parts per million. And if you make this a calculation of temperature based on experiments for titanium and zircon, you get apparent temperatures in the range of 650 to 750 degrees, which I don't necessarily think are accurate, but that's what you get. And if you do the same calculation on the Moon, where the concentrations are on order of 100 ppm, You get temperatures that are much higher because the lunar magmas were not water saturated and were genuinely a lot hotter. So this is another indication that these Jack Hill zircons are not from the moon. They genuinely are terrestrial and representing different processes. Are these zircons from ocean crust? We'd really like to know if the zircons represent continent-like bodies versus mafic crust. And there are a lot of zircons forming today on modern ocean crust. And this is a brand new study that's not actually out yet. It's in press by Craig Grimes, working in my lab, of oxygen isotopes from a wide range of modern ocean crust, the Mid-Atlantic Ridge and the Southwest Indian Ridge. And we see that both in the plagiogranites and in the oxide gabbros, that we have this very narrow range of oxygen isotope ratio that is mantle-like. These are magmas that bring their oxygen with them from the mantle, and the zircons crystallize before any crustal near-surface exchange. And so that's the histogram for all of the zircons from modern ocean crust. And it's, again, very different from the Jack Hills. So the oxygen isotopes are not like ocean crust, but there's two other discriminants. Lithium, we also talked about, is very dramatically different. And then there are a range of trace element discriminants that have been published. This is from a paper by Grimes et al. 2 years ago, where he shows that continental zircons fall in a field that look like this, as uranium versus terbium. And the ocean crust zircons are shown here in blue, and that the Jack Hill zircons in this discriminant diagram, again, are indicated to be of a continental derivation. So they're not ocean crust zircons. So are they from a granitic rock, using the term broadly, which would include things like tonalites, trondhjemites, and granodiorites? And again, the lithium seems to be an important indication here. Originally, when we published this paper, we had a very small histogram of data. We've now looked at a large number of igneous rocks from the Archean, the TTG suite, which is the most reasonable, I think, hypothesis for where these zircons came from. And we see that the lithium concentrations are very similar in TTGs and then these mildly enriched igneous rocks that are called silicotoids in Archean, and that they look like the Jack Hills. And that the only thing that's different here about the Jack Hills are these low delta 7 values, which, if faithfully preserved, are consistent with much more weathering on the earliest Earth. Okay, are they from real granites? There are a number of papers written that have proposed this, and one of the lines of evidence, probably the strongest line of evidence suggesting that these formed from wet granites, are these titanium temperatures. And I would call these apparent temperatures because this is uncorrected. And this is the range that we get, and Harrison et al. Also report a similar range in titanium temperatures. We don't disagree in the titanium compositions, merely in the interpretation of what these apparent temperatures mean. I would, rather than get into the whole titanium and zircon thermometry question, which I'm happy to talk about later, I just want to point out that there are large suites of mafic rocks that are indistinguishable based on their titanium composition from the Jack Hill zircons. And in fact, gabbroic rocks from the Sierra Nevada are these black boxes, and you cannot distinguish them. There are other terrains where the gabbroic and mafic rocks have more titanium in the zircons, but there are vast areas of the crust where you cannot distinguish the rock type based on these compositions. The argument has been that, well, 650 to 700 degrees, that's the temperature of melting of a wet granite. But the fact is that assumes that the thermometry is accurate. And if you just look at the composition, you cannot distinguish these. In fact, in the Sierras, the granites are very much lower in their titanium composition, yielding these apparent temperatures, which I think are unreasonable for crystallization of granites. So the titanium does not tell us that these are from true granites. I think I would stop with saying they are granitic. And do we have relics of rock? We don't, in fact, know the age of most of these clasts, so we don't know if some of them may be older than 4 billion years. But when you look at the zircons themselves, you see minerals included within the zircons. So even though that's only 200 or 300 microns long, we see things like quartz that are included within them. We see suites of minerals that, in fact, mean that the zircons themselves are very small rocks. And so Here is that zircon. Here are two inclusions, greatly magnified. This is the list of minerals that have been reported by us and by other people in these zircons. And many of these are minerals, for instance, quartz is fairly common, that suggests that this was a silica-saturated magma that these zircons formed from. But it doesn't tell us how much of that magma existed. And it also doesn't necessarily tell us how well they're preserved. So we've done oxygen isotope analysis of these inclusions, and some of them appear to be preserved and be magmatic. Others are clearly reset. The same story comes from the chromium content of included micas. So this question of when did the first continents form is not yet answered by this suite of samples. It suggests that we have granitic rocks, but it doesn't tell us whether we have domains of granitic rock this big or whether it was as big as the Yilgarn craton. That is, in my opinion, still an open question. And where did the earliest rocks go? If it's correct that there was this acid sauna before 4 billion years ago, the suggestion would be that rather than being destroyed by impacts, which is the common hypothesis for the earliest rocks, they may have simply been dissolved away by the intense weathering. 2 minutes, okay, I'll go quicker. We'll have to skip over the late heavy bombardment. When did the Hadean end? The lithium concentration, the lithium isotope ratio, and the oxygen isotope ratios all suggest that these relatively clement conditions existed as early as 4.3. So the Hadean, in terms of really hell-like conditions, if that's what you think Hadean means, was over by 4.3 and possibly by 4.4. The Hadean was very short, and the period where real magma oceans were on the surface of the Earth was probably much shorter yet, possibly just millions of years. And so this informal boundary of the Hadean at 4 billion years is too young. It's 4.3 or 4.4. And I would argue that the best definition for the Hadean is when the surface got cool enough that the steam atmospheres condensed, because that was a worldwide event of very profound geologic importance. Okay, it could be, in fact, that rather than being an acid sauna, it was a snowball Earth, which has interesting implications for the environments where life might have evolved. And I will just go quicker and conclude with this. These early zircons are not the same as what we find in mafic and primitive and extraterrestrial environments. They are, in many ways, consistent with what we see in continental crust today. And so I would say that this is proto-continental crust. This is the beginning of this differentiation process. And whether a continent was actually formed before a billion years or not, we don't really know. I think the evidence for liquid water oceans is very strong as far back as 4.3, and we simply don't have enough samples to say whether it might have been a little bit earlier. And I think there are a whole lot of other questions here relating to the tectonic significance of these rocks and some of the details of how they formed. So I'll stop there. Thank you. Jill?
So what is the story with these diamonds?
Well, we've looked very hard at the diamonds. Some of you may know there have been 2 papers published in Nature now reporting diamonds fully contained within the zircons. And then there have been carbon isotope measurements made on the diamonds, and the delta C13s range from about -5 to -50. And -25 to -30 is what many people would say is a signature of biological life. And so this has left open the question, is there fossil life in these zircons? We've looked at all of our zircons that are older than 4 billion years, which is a suite of about 200 of them, in 4 different labs now by laser Raman, which is the technique of choice. We have found diamonds in quite a few of the samples, but they are always and sometimes they're below the surface where we look at them, but they are always in tubes that connect to the surface elsewhere. So we have never found diamonds that are actually isolated from the surface of the sample. And since we polish our samples with diamonds, we're unprepared to say that these are natural. We've also sent 500 zircons to Novosibirsk, which is the first place to recognize diamonds in metamorphic zircons. And they've not found any diamonds in those samples either. And the UCLA group reports that they've looked at 400 of their oldest zircons and haven't found any diamonds either. So I haven't looked at the diamonds that the paper's written about. those authors have chosen not to share their samples with us. So I don't know what they have, but we've not been able to reproduce the observation.
Are those compositions consistent with the abrasive diamonds?
Well, you mean the isotope ratios? Yeah. I don't think the isotope ratios mean anything, because when you find these diamonds, they're in the bottoms of holes. They're always plucked. And if you're making a precise isotope measurement, relief is a big deal. The beam gets distorted when you analyze in the bottom of a hole. And so I'm hesitant to say what those carbon isotope data mean. There are laser Raman bands that are interpreted by Giesler et al. To mean that they're not polishing powder. And so they've done their best to distinguish this. And so I really don't know what they're looking at. But for our diamonds, when we find them, Hiromi Kanishi at Wisconsin has actually cut these out with a fib and looked at them with a TEM. And the diamonds are typically 1 to 3 microns. They're often very well sized. They're very tightly packed together, and they're not bonded. Typically, they're not bonded to each other, and they're not bonded to the zircon. So they look like they're just hammered in there. Yeah.
Question about the question that you raised up there, life at 4.3 billion years, or even something
Sure.
later. Is there any evidence that the zircons may have harbored sites that supported life in some fashion, either chemosynthetic or early photosynthetic level?
That's an interesting question. I think the diamonds are the only evidence that anybody has interpreted as being indicative. But the zircons themselves form from a magma. And so no one disputes that the zircons formed at temperatures around 700 or 800 degrees centigrade. And so they are carrying a chemical signature that formed earlier and was buried and inherited into the magmas. So you wouldn't expect to see anything except maybe in the last 100 million years of the history of these zircons, when they're now on the surface again. So I don't think that, with the possible exception of preserving primordial carbon, I don't think there's much we'd expect to see. Yeah. Warren, did you?
Yeah, could you say a little bit about the implications of your findings and interpretations for the early Earth's thermal budget? I mean, there are all these heat sources, right? Or formation.
Yeah, yeah,
life,
yeah.
et cetera, et cetera.
Well, ironically, the geophysicists have, for 150 years, been telling us that the Earth cools very quickly. Lord Kelvin had that part of his calculation correct. And the modern papers, there's quite a bit written on this, suggest that if the Earth was hit by Theia and the moon formed and the core segregated all at that time, the Earth probably would have melted and it could have gotten up to 8,000 C. And so if you had an event like that, the calculations are that the Earth would crust over in between 1 and 10 million years. So even if you melt the Earth all the way to the core, when it's magma on the surface, it radiates to space at something like 10 to the 5th times a higher rate than what it does when it's solid. It's glowing. And so the crust starts to form. And so then the question is, what is one's model of what happens after it starts to crust? Do these slabs sink like in the Hawaiian lava lakes, and you have a complex history for a long period of time? And of course, they're being hit by fairly large meteorites in this early period of time, which could be puncturing it. But so the crust starts to form, and depending on how you model the stability of the crust and what you think about the atmosphere and the insulation of the atmosphere, you can run these models in a lot of different ways. But it's a very reasonable model to think that within 100 million years there was quite a thick crust, and there may have still been magma at 400 kilometers depth, but that there was a fairly thick crust such that the Earth was now the dominant heat budget on the surface of the Earth was solar radiation rather than geothermal radiation. And I'd be interested in what you think about the xenon closure age of the Earth, but that's usually put, I think, at about 4.45, which is 50 million years earlier than our first zircons. And so if that was the last major outgassing of the Earth, this is right in line with that. There have been zircons now dated on the moon that are 20 to 40 million years older than 4.4, and that's the oldest. So the oldest zircons on the moon are pretty similar to the oldest zircons on Earth now. So I think it holds together that this is really when the Earth started to form a solid crust, and portions of that crust as old as 4.4 have obviously been stored someplace because these zircons didn't go back to the mantle. They would have been destroyed. So those 4.4 billion year zircons means that there was a little bit of buoyant crust someplace that didn't get subducted. Yeah. Paul?
That feeds right to a question I have, which is whether there are any active programs underway, to find other Jack Hills. I mean, are there other Jack Hills?
People have been looking all over. To my knowledge, there are about 5 pre-4.1 billion year zircons that have been found elsewhere in the Earth. There's one from Acasta. Iizuka published a paper a few years ago on one zircon. There's one at 4.17 from Aquileia in Greenland. There's one from the North China block, and I think there's one from Enderby Land, but I haven't seen that paper. So people are looking, and genuinely there's this concentration in the northern Yilgarn that we haven't found anywhere else. They aren't turning up in the Pilbara just to the north, which is interesting because some people think that those terrains formed together and then separated and came back together again at the Capricorn orogeny. And so we aren't seeing that. The sedimentology in the Jack Hills suggests that the sediment transport this direction was north to south. And so wherever these zircons came from was basically out to sea. So we don't know where to go look for it.
Well, then you have the disappearance of that mode stratigraphically.
Well, then there's the younger sedimentary rocks. But if we just stay in this older siliciclastic package, the sediment transport direction appears to suggest that they came from the north. Yeah. Question way back. I'm sorry? The delta 17 in these zircons? Yeah, that was in one of the earlier slides. I went over it pretty quickly. These are all zircons that are older than 4 billion years. So that's delta 017 versus delta 018. So they're terrestrial by this indication. Yeah. This is I would have been blown away if they weren't, but. I'm sorry. The lunar zircons also fall on this line within like a hundredth of a per mil. That's the moon and the Earth. This has been a big surprise to people, but the moon and the Earth have identically the same oxygen, all 3 oxygen isotopes, which the best interpretation of that is that the moon and the Earth were homogenized at the time of this impact. Yeah.
Could you refresh my memory? What is the estimated date that this impact occurred that led to the formation of the moon?
That's been pretty controversial, and there's been a lot written just in the last couple of years. But my understanding, this is all based on lutetium hafnium, and my understanding is that it's within 5 half-lives of the formation of the solar system, which is about within 50 million years. So earlier than 4.5 would have been the impact, within the 30 earlier than 4.5. And so our oldest zircon is 100 million years younger than that.
Because essentially, if you had complete fusion of that
Yeah.
point, all previous history is essentially quite
Yep.
academic anyway.
That's what we think. Well, and that's probably the reason for this line. I mean, if you analyze meteorites, of course, you see a huge range of compositions along a slope of one line as well as this, and that's probably because the Earth was homogenized. The material that accreted to the Earth probably had that range of what you see in the asteroid belt today.
John has a
Yeah.
question.
Yeah. Right. Well, do you get a different age from calcium tungsten?
No, hafnium tungsten system.
Oh, sorry. You're right. It's hafnium tungsten. That's right. I did misspeak. Yep.
Is it feasible to measure tungsten isotopes?
I think this is going to be a sample size issue. With a single zircon weighing 5 micrograms, the amount of tungsten is going to be so small. I don't know what you need to make this measurement. A nanogram? My guess is that you need a gram of zircon to make that measurement accurately. Yeah.
just had one quick question,
Yeah.
and then other people go.
Yeah.
So much of the interpretation is based on this assumption that the diffusion rates are very slow in these materials. So an obvious question is whether you can take, in the instance you have a sharp gradient in concentration of enrichment, can you heat up these materials and actually look at the in situ diffusion rates as a function of temperature, just to see if you could have the alterations that you're obviously worried about?
This is what goes on at the RPI lab, at Bruce Watson's lab, and they've done a number of experiments on zircons over the years because it's so interesting. But they have calibrated oxygen diffusion, now lithium, rare earths, uranium and lead. You know, there's a whole suite of studies where they basically take a zircon and they heat it up in an environment of contrasting composition and then measure the profile that develops into the zircon. And there's a lot of questions about what's really going on when you do these kind of experiments, but that is the state of the art today. Yeah.
Okay, so if there are no more questions, then let's thank John for his
Thank you. So I was warned to turn this off.